Here, we're going to learn how to convert Cartesian coordinates to polar coordinates. We start with the Pythagorean theorem, which states that of the two sides of a triangle, of a right triangle, that x squared plus y squared equals r squared. If we take the square root of both sides, we can write this as r equals the square root of x squared plus y squared. This equation is generally applicable regardless of what values we have for x and y. Things are a little bit more tricky for finding the angle. For finding the angle, we typically use the tangent function. We take the inverse tangent of both sides and get theta equals the inverse tangent of y over x. This works very well, but has one shortcoming. There's an ambiguity as to whether we need to add 180 degrees. I'll get back to this in just a moment. Let's do an example first. If we start with the point coordinate 3, 4, well then, to find the radius, we do 3 squared plus 4 squared. This gives us 9 plus 16, which gives us 25. Take the square root of 25, we get 5. The radius is 5. Likewise, if we want to determine the angle, we take the inverse tangent of y, which is 4, over x, which is 3. And we evaluate this, and we get 53.13 degrees. Now, likewise, we can do an example where we work out we'll do 2, negative 5. Here, to find the radius, we will take 2 squared plus negative 5 squared, which is the square root of 4 plus 25, the square root of 29. So r equals the square root of 29, or approximately 5.39. Likewise, our angle is determined from the inverse tangent again of y, which is negative 5, over 2. If we evaluate this, we get the inverse tangent of negative 2.5, which is negative 68.20 degrees. Hence, our final answer would be, in the form of r at an angle of theta, 5.39 at an angle of negative 68.20 degrees. One more example that illustrates the a certain difficulty with this formula. We will notice that the points 2, negative 5, and negative 2, positive 5 would result in the same angle when we use the tangent formula. Whether we do negative 5 over 2, or 5 over negative 2. Gives us the same answer. In this case, we need to be aware of what quadrant we're ending up in. The ambiguity may be settled this way. We can first of all pay close attention to what quadrants we're dealing with. So in which case we may need to add 180 degrees. Always 180, not more, not less. So if we end up in quadrant 1 or quadrant 2, we're typically fine. Depending on but we need, as long as we need to pay attention. If we end up in quadrant 2, as long as our x is negative and y is positive, we have the correct value. If we get a value down here for the angle, then we know we have the wrong angle. For example, if we have the point negative 6, 2, to find the angle, I would do 2 over negative 6. This naively gives me an angle of negative 18.4. Should we believe this? Well, let's graph this point out. It is negative 6 over 4, 5, 6, 2 up. The angle is over here. Whereas 18 degrees would be right here. In this instance, we need to add 180 degrees to this. So we take negative 18.4, add 180 degrees. Gives us the correct angle of 161.57 degrees. There is a second method we can use. If we don't want to pay attention to whether our x is positive, x and y are positive or negative, we can also use the formula that tangent theta over 2 equals 1 minus cosine theta over sine theta, or its sister formula, sine theta over 1 plus cosine theta. If we rewrite each of these formulas, we can get an expression for theta that has no ambiguity with regards to which quadrant we're in. These formulas will always work. They aren't often used because they're a little bit longer than the first formula we went over. They are, however, always correct. So if this confuses you or gets you stumped, these will always work.